first lesson in this course is about functions and relations. Now, relations is something that you've already learned about in grade 9 and 10, and we're going to extend on that idea in grade 11. A relation, officially, the definition is it is a set of ordered pairs. So here, for example, is a relation, and this is a set of four ordered pairs, 0, 3, 2, 5, 4, 6, and 5, 10. Now these curly brackets on the outside is the symbol that we use in math to denote a set of objects, or in this case, a set of ordered pairs or a set of numbers. Now, there's many different ways that you can represent a relation, and you've seen all of these before. One way is using a table of values to identify the x values on the left and the y values on the right. And in turn, this shows each of your ordered pairs that is part of that relation. Another way to represent a relationship would be on a graph. And again, you've done this in grade 9 with linear relations and in grade 10 with quadratic relations. So for example, a parabola on a graph is a relation because if you look at it, there's actually an infinite number of ordered pairs that would satisfy that relationship on the graph. Another way to represent a relation would be using an equation. And for example, a linear equation, y equals 2x plus 1. This equation represents all of the x and y values that together form the ordered pairs that would satisfy this relationship. A function, which is the main topic of this grade 11 math course, is actually a special type of relation. But for a function, every x value has only one corresponding y value. It cannot have more than one corresponding y value. So here's a relation. We're going to test to see if it is possibly a function or not. So we've got this set of four ordered pairs, 0, 3, 2, 5, 2, 6, and 5, 10. Now, what we're going to do to figure out if this is a function or not is we want to see for every x value, is there only one corresponding y value? So we're going to line up the x values on the left and the y values on the right, and we're going to connect the two using an arrow for every ordered pair. For example, one ordered pair is 0, 3, so we're going to connect the 0 on the left to the 3 on the right. Another ordered pair is 2, 5, so again, connect the 2 on the left to the 5 on the right. You don't need to repeat values if they're repeated in the ordered pairs. This type of diagram is called a mapping diagram, and this is one tool that we can use to identify whether something is a function or not. Now, it is still a relation, but it just might not be that special type of relation. Looking at this diagram in the middle, we've actually got two arrows coming from the 2 on the left and going to two different y values. So this means that the x value of 2 is associated with two different y values in this relationship. Based on the definition of a function, which is above, every x value can only have one corresponding y value. So this is actually not a function. It's still a relation because it's a set of ordered pairs, but it's not considered to be a function because the x value 2 has two different y values that correspond to it. Here's another example, and again, we're going to test to see whether this is a function or not. So we've got the ordered pairs -9, 2, -2, 2, +4, -2, 13, -2, and 0, 0. And again, we're using the curly brackets to indicate that that is a set. Okay, so we're going to set up our mapping diagram. The x values go on the left, and they're connected by an arrow to the corresponding y values on the right. Again, a reminder, you don't have to repeat values if they are repeated. So you'll notice that there's the first 2 points both have a y value of 2. So I've just got the first two x values connected with arrows to the one y value of 2. Okay, and we finish our mapping diagram. So we should have 5 arrows for the 5 ordered pairs in our relation. And if we look at this diagram, there's not ever 2 arrows coming out of one x value. There might be 2 arrows pointing towards one particular y value, But the definition of a function is concerned with whether each x value has one corresponding y value. Well, that is true in this mapping diagram because there is not two arrows coming out of any particular y value. Each x value only has one arrow coming out of it, meaning it only has one y value associated with it. So this relation is actually a function. Here's a couple more examples. Sometimes we might want to take a look at relations that are on a graph. And if we're given relations on a graph, a mapping diagram isn't all that useful because we would have to convert the graph into a set of ordered pairs first. So what we use is the vertical line test. Now to use the vertical line test, you're going to take a vertical line and draw it vertically anywhere on your graph so that it crosses your relation. If that vertical line, no matter where you move it on your graph, if it only ever crosses one point, then your relation is a function. So in the case of this linear relation on the left, you can see I've drawn in 3 different vertical lines, but I can move that vertical line anywhere on that graph, and that vertical line will only ever cross my relation at most one time. And so that is what makes that a function. On the right-hand side, same idea. If we use this vertical line and we draw it anywhere on our graph, if it only ever crosses that parabola once, or at most once, then it is a function. So this parabola is indeed a function. If we take a look at this circle, on the other hand, we could draw in a vertical line on either the far left or the far right side, and that vertical line would only cross that circle once, but anywhere else that we draw on a vertical line on that graph, the vertical line is going to cross the circle in 2 locations. So since there's a vertical line that crosses in 2 locations, that actually means that for that particular x value, where that vertical line is located, there's 2 y values that are associated with it. So that circle is not a function. Now for functions, we have a special type of notation that we use to identify when an equation is a function or not a function. If an equation represents a function, we can use the term f at x or f of x, and the notation is f and then with inside brackets the x beside it. It's not f times x. It's saying what is the value of the function, or what is the value of that relationship or equation at a particular value of x. Okay? So this is a new notation that you probably haven't seen before. But essentially, it's going to go in place of the y in an equation. So here's an example. Let's say we have the equation f of x is equal to x squared minus 3x plus 5. Now, we know that this equation represents a function because this is actually a quadratic equation. And any quadratic relation, if you think about it in your mind right now, any parabola that you can draw on a graph will be a function because it will always pass the vertical line test. Okay? And so because this equation is quadratic, we know right away that it's a function, and we can use this function notation to identify that it is a function. Now, using this function notation, we can do things like plug in values of x and solve for what the function value is at that x value. For example, f of 1 means that we want to find what is the function value when x is 1. So we substitute an x value of 1 into the equation and then simplify. So this will tell us that the function value when x is 1 is actually equal to a value of 3. This also indicates actually an ordered pair as well that's on that function. Here's another one, f of negative 3 using the same equation. Same idea, we want to take that negative 3 and substitute it in for the x value in the equation. So what is the function value when x is -3? Or what is the y value when x is -3? You can think of it that way. So here we get that the function value when x is -3 is 23. And again, this would represent an ordered pair on that parabola, which would actually be -3, 23, the x and the y value. Here's another example of function notation. Let's say we have f of x is equal to -7x plus 11. Now this happens to be a linear relationship or linear function. Again, any line that you draw would be a function other than a vertical line. A vertical line would not pass the vertical line test to be a function, but any other linear relation that you could draw on a graph would be a function. So this time we want to find out what is f of x plus 2. So we want to know what is the function value, or what's an expression for the function value when x is x plus 2 now. So we're going to take all the x values that are in that equation and replace it with x plus 2. Okay, now in this case, we won't be able to get a particular value as an answer, not a numerical value, but we will be able to get an algebraic expression for our answer. So we expand this, -7 times x, -7 times 2, and then collect like terms, and we get an expression of -7x, and then -14 plus 11 is -3. Now, it doesn't always have to be x and y values that we're working with. We could have other variables as well and still use function notation. So here's an example using, let's say, height and time. So h of t is equal to 3t plus 4. And let's say I want h of happy face. So I want to know what's the value of the function when t is equal to happy face. I can put in anything I want to using function notation. Okay, so I can put in numbers, letters, variables. I can put in happy face. The idea is that we're substituting whatever is replacing that t or that x in the brackets. I'm substituting that into my function equation. So here, if I substitute in happy face for t, I'm going to have 3 happy face plus 4. Okay, here's another type of question you might see using function notation. And function notation is going to be an idea that we carry on throughout the rest of the course. So here we want to determine the value of t if h of t, so if the function value, or you can think of that as just if the height at a particular time is equal to -5. So we're going to take -5 and substitute it in for h of t this time. Okay, so we get -5 is equal to 3t plus 4. And then we've got an equation that we can solve for t. So rearranging, we end up with -9 is equal to 3t. And then divide both sides by 3 to get -3. So that tells us that when the function value is equal to -5, the t value would have to be equal to -3. Okay, here's a graph with the function, and you can use function notation to identify coordinates on a graph as well. So let's say using this graph of this function, and it passes the vertical line test, so it is a function. There is only ever one possible y value for any x value. Right, we've got the scale on the x-axis. We want to find the function value when x is -2. So what we do is we go to -2 on the x-axis, go down to wherever our function is located, and we see that point located there, and we want to know what is the y value for that point. So what's the y value when x is equal to -2? Well, it happens to be -2 as well. So that again gives us coordinates. That the coordinates of that point would be -2, -2. Okay, we can try another one. What's the function value when x is equal to 3? So again, we go to 3 on the x-axis, go up to that point or down, depending on what your function looks like. Go across to your y value, it happens to be 1. the function value at 0, or f of 0. Again, we go to 0 on the x-axis, go up to the point that happens to be at 0, 2, and so the function value at 0 is 2.